Today we'll start from the probability current for step function potential. So in this case, we split the space into two different regions, region 1 and region 2. And the energy of a particle like electron is larger than potential barrier height, V0. And here in region 1, wave function is psi 1. Region 2, wave function is psi 2. And we found that when we presume the particle is coming from the left, the wave function representing that right propagating wave is this part, a to the I k1x, and then b to the minus I k1x represent the left propagating wave, and psi 2 is the transmitted part of a wave. And then each part, like a right propagating wave, left propagating wave, transmitted wave, corresponding to different components of current. So there is incident current Ji, reflected current Jr, transmitted current, and those are actually probability current, which was defined here. So this is the definition of probability current, and we have its wave function psi. Psi star is the complex conjugate of wave function psi. So incident part, we have this wave function, we put this into here, then we take the complex conjugate, so complex conjugate will be A star. A is said to be real number, so A star is just a real number, and then e to the minus I k1 x to be psi star, right? And then we put that psi here, and then psi star, we put those and then calculate, then we can calculate Ji. Then you will get this one, Ji is equal to E h bar k1 over m, then a square. So this is actually the homework problem. Okay, calculate Ji, Jr, and Jt. Okay, and those c square and b square were calculated previously. Here, transmission coefficient, reflection coefficient are given here, T and R. T is defined by Jt over Ji, and then we see that it is not just the ratio of amplitude, it must be multiplied by this one, K2 over K1. Then we will get this one, 4K1 K2 over K1 plus K2 square, so that we see the numerator is smaller than denominator. This is less than 1. Okay, so now it is reasonable, right? Yeah, it cannot be larger than 1 because it is transmission. If it is larger than 1, it means the amplification. A reflection coefficient is defined by Jr over Ji, and surely we take the absolute value. Then we can get the b over a square multiplied by k1 and k1. So reflected wave, if we think about it, they are actually in the same region. So those region is both represented k1. I mean, incident wave and reflected wave is both represented by k1. And here in the case of T, we got the ratio between Jt and Ji, and then in the case of Ji incident current, It is in region 1, so it is represented by K1. In region 2, it is represented by K2. That's why you will get this K2 over K1. Yeah. So in the same region, actually K1 over K1, so they subtract with each other. We just get this one. If you sum them up, T plus R, then you will get 1. So this is expected from current conservation. So now it works well and reasonable. Tunneling through a square potential barrier. It's becoming a little bit more practical now. So the square potential barrier previously we solved. Now we consider the unbounded state where the energy is larger than V0. V0 is the potential barrier height. So we split the space into 3 different regions: region 1, region 2, and region 3. In region 1, the wave is instant from the left, like this, and then it is reflected. And then in region 3, it goes through and then it propagating toward the right hand side. So we only have this part, right hand side, right propagating wave. Here you have right propagating wave and left propagating wave. So for the case when energy is larger than V0, you have 3 different regions and now you have 3 different wave functions. Alright, so this actually we calculated before. Well, basically we solved the Schrödinger equation. Yeah, just as a reminder, we additionally added the time-dependent part here. But here we just have time-independent part. We go through time-independent Schrödinger equation to get this. These are results. And then we consider the boundary conditions at x equals 0, where psi 1 and psi 2 are continuous, right? And then their first derivative is also continuous. So that we have these 2 equations. Likewise, at x equals L, also we apply the continuity condition, or boundary condition. So wave function in region 2 psi 2, wave function in region 3 which is psi 3, they are continuous and their first derivative is also continuous. So that we have these 2 equations. Then you have actually matrix equation, right? So that we have this matrix formation. For example, if it's A and B, it should be 1, 1, K, minus K, right? Equals to CD. Then it is 1, 1, alpha, minus alpha. And then you have another equation between C and D in terms of F. So here you can get another equation like C and D equals to here e to the I alpha L, you can write it down, e to the minus I alpha L, C then alpha, e to the I alpha L minus alpha e to the minus I alpha L, right? For the case of f, actually, one is e to the I k l, then k e to the I k l. Okay, so and then you can connect this equation C and D can be replaced by F equation. Eventually you can get the ratio between D and A, F and A. Alright, so that T and R can be calculated. Yep. Here actually you can note that originally we calculate the transmission and reflection based on this current ratio like this. This one you also need to consider current ratio, JR, JI. Surely we take the positive values. But here, actually, it's just the same with the amplitude ratio because in region 1 and in region 3 we only care. So incident wave and reflected wave, they are in the same region 1. Incident wave and transmitted wave, they are different regions, but their K value is just the same because potential height is same, set to be 0 in both cases. That's why actually we are ignoring the ratio of K here. Okay? Yeah, K here. We are ignoring this part. Then you can calculate this one. So basically these are not that difficult in terms of logical structures, but you need to go through some tedious mathematical calculations. So please give it a try yourself, and this will be also the homework problems. All right. And then yeah, T and R previously calculated. So we consider their structure here. So in classical physics, if energy E is larger than V0, then the particle slows down as it passes through the boundary, but is otherwise unaffected. In other words, in this case, the energy E is larger than V0. And then classical physics, R is 0, T is 1. Everything is going through the barrier. But it is not in quantum physics, right? T could be varied, R could be varied. But we have this same condition with classical physics only when, okay? I should say only when. This one goes 0, right? If it goes 0, then yeah, numerator, denominator, that becomes the same, and T becomes 1. So sine alpha L is 0. That's when alpha L equals to n phi. So, but this is repeated every time when the alpha equal to n phi over L. So this is related with the energy value actually. Alpha is related with energy value. So as the energy goes from here to go above, it is repeatedly transmission could be 1. So there is oscillatory behavior of R and T as a function of alpha L. Okay, surely it is both function of the alpha and L. So even though we set the same value, so the energy is fixed, but still if your barrier thickness is changing, then alpha L, multiply them, then sometimes it could be m pi, it could be not m pi, so R and T should show the oscillatory behavior. And then we can apply the same ideas to the case when energy is smaller than V0, like this. Energy E is now smaller than V0. So, but with minor mathematical changes, because wave function shape will be a little bit changed. So that is another question you can calculate. Wave function structure is almost the same, right? We just split into 3 different regions. Then we go through time-independent Schrödinger equations, right? Then we go through almost the exact procedures of calculating, F over A and B over A. Then you can get the values for this one. And okay, the general shape of R and T as a function of this one, V0 over E and L. So this is actually the barrier height as a function of barrier height. Actually, well, let's say we just fix the barrier height, now we change the energy values. Then still we can change this V0 over E. And then L could be changed in semiconductor devices. For example, this is often found. The square potential barriers very easily made based on semiconductor materials. This L could be like 1 nanometer. You can choose any values actually, sometimes like 100 nanometer. You can almost continuously change the barrier thickness in that way. Then you can change T and R in oscillatory behavior, with oscillatory behavior. This reminds us of the interferences of waves like light waves because of reflections from the barriers at the interface. So this one and this one, we are just drawing the curves as a function of V0 over E or as a function of L. Okay, then the solid line on top is the transmission, and dashed line on the bottom is the reflectance or reflection. Then if we add them up, R and T, it is said to be 1. And also we see that there is some oscillatory behaviors, going up and down, going up. That is the oscillation. And here oscillation behavior is most simple because as a function of L you got the sine function, so exact oscillation, very simple oscillation can be observed. Still R plus T is said to be 1, right? Okay. So wave function itself we already calculated previously, but here issue is you go through the procedure to calculate F over A and B over A, and those are actually often very useful in semiconductor materials. Semiconductor materials, you will see these tunneling problems, so many cases. Okay, and it could be larger than barrier height or sometimes smaller than barrier height. For the bound state with energy E is smaller than barrier height V0, then you have this situation. Okay, so the same problem we have. Wave is incident from the left, so we got that right propagating wave, and it is reflected at the interface. We got left propagating wave now, and then we pass through the barrier. Then we have transmitted wave. Potential is set here, V0. Then you go through the same calculation, but please note that Previously energy E was larger than V0. Now energy E is smaller than V0. So originally sine function becomes the sine hyperbolic function. You can guess that, right? The imaginary number is now changed into real exponential function, so that sine function becomes sine hyperbolic function now. It's not that difficult actually, you can calculate yourself. Then gamma is defined like this. Again, here actually R and T, sum them up, we have 1. But now we don't have oscillation behavior anymore because it is not sine function. It's sine hyperbolic. Sine hyperbolic is the combination of exponential function. So we see the exponential decay part and the exponential increasing part. Okay, so we just drew this curve here. So it's a function of energy here, and there's a function of L. But please note that in classical physics, when energy smaller than V0, then there is no transmission. Everything should be reflected. That's the classical physics. But in reality, in reality, it's not the case. The transmission, is here. Reflection is here. Reflection doesn't need to be 1 actually. As a function of energy E, energy E, it is changing. Okay. So transmission exists. Transmission is solid line exists. So this indicates the tunneling, something passing through the barrier. Okay, as a function of L, very thickness leads to small transmission. The solid line is transmission is decreasing, but still there is some small portion of transmission, even though there is a barrier. So that is often found in semiconductor materials. So the general trend of T and R on the right, T decays exponentially as the width of the barrier increases. This transmission function, it's a function based on sine hyperbolic function, and this is the form of sine hyperbolic. This is x and this is sine hyperbolic x. You multiply that, you take the square, then it will be more rapidly increasing, right? So sine hyperbolic square, you take it as sine hyperbolic x and you take the square. So it is like this. So based on this equation, you can draw the curve for this. For infinite V0, and the barrier V0 is increasing a lot, then look at this gamma. Gamma becomes very large. Then sine hyperbolic is extremely large. It is diverging. Then T must be 0, like this. Then for sufficiently large V0, it is not infinite but sufficiently large, then because this exponential function, if we compare exponential x and e to the minus x, when x is large enough, then we can ignore this part. So it is a function depending on mostly on e to the x. So we only choose this part, and sine hyperbolic function is changed like this. So we simplify it like this. So 16 by e v0 minus e over v0 square e to the minus 2 gamma L. This one can be easily calculated in different way, as shown here. It is called WKB approximation and tunneling. WKB method can be used to find an approximate solution to any one-dimensional differential equation. So actually, it's a little bit complicated, but previously we introduced concept. The barrier is arbitrarily given, and you have electronic energy. Let's say energy is set here, and the intersection is given at x equal x1, x equal x2, and the carrier will pass through. Then you can calculate the transmission or tunneling coefficient. There is very complicated mathematical procedures, but we don't need to care about it for now. We just accept the final result, and this is very useful. And when you see this kind of formula in research papers, and please note that we integrate from x1, x2, and within the square root. This one is important. Vx minus E, and M is the also important. It is the effective mass of semiconductor materials. So x1, x2 are points or intersections where energy E is equal to Vx. So if we apply this idea into the square potential barrier, just like we discussed before, based on the probability current, then you will get the same result. Look at this. Put this V to be V0. This is V0. V0 minus E, so this is constant. And then integral is from 0 to L. So we just multiply it by L into here. Then you will get this one. So we only have exponent. Yeah, e to the minus 2 gamma L. So same with the case with sufficiently large V0 case. So you can see that this is actually not exact. It works only when the potential is large enough. So that's why it is called as approximation. So, but it is quite simple. We don't need to calculate the wave functions in different regions, and we can apply any arbitrary potential shape. So it's useful, it's much easier, so people are using this. Well, you just need to remember the basic structure here. Integral between x1 and x2, and square root, and this one. Yeah. So based on this, actually we calculate the tunneling coefficient or transmission coefficient. And one of the most important problem is actually named as ohmic context. The meaning of ohmic context, it is okay even though you don't understand the meaning of ohmic context. It's the basic topic of semiconductor devices. There are two different contexts between semiconductor and metal. One is ohmic contact, where current flows in both directions, right hand side, left hand side. There's another one, Schottky contact. Current flow along only single direction. That's the idea of diode. So you might need to use the Schottky contact to form certain structure of diode, but you don't need to know the details for now. But here important point is, when you have the contact between metal and semiconductor, then surely the band is tilted only in the semiconductors. Fermi energy is changing in semiconductor side. Metal, doesn't show the change. Well, if you need to understand those, then we might need another semester. So let me skip that part. But point here is, we see this problem so many times. Let's say energy E for the electron is at Fermi energy, and it has the barrier. And then let's say we consider the tunneling parameter. Then the intersection here 0. Look at this. if we set this energy EF, and this is the approximation of potential shape. Pi is actually this barrier height felt by electron, and then EF, Fermi energy, then minus E epsilon. Epsilon is actually the electric field in semiconductor side, often called as deflection field. But we don't need to know the concept for now. But epsilon is the electric field, E is the electron charge, X is this dimension, this direction. Then previous tunneling formula we have, then we put this into here, okay, and then go through the integration. So I think this is one of the most important problem you have in quantum physics, and this is very useful. I said very useful. Everybody calculate this, and I'm absolutely sure all of you eventually find this formula in your devices at some point. It is that important. For example, there might be some quantum instead of matter. That's the case of most of semiconductor devices. Quantum, and it could be barrier. Always you have the bias, external bias. So the quantum potential is tilted, quantum energy is tilted, barrier is tilted. So it is actually a little bit more complicated like this. They are tilted under the electric field like this. Then electron energy, it is set by the bound state, like lowest bound state of quantum, second lowest state of quantum, something like that. And that quantum electron will go through the barrier most of cases, and that's the source of leakage current. Then if the leakage current is too large, devices break down, so it is important to understand. So this happens. So same problem we can apply. You said it is not Fermi energy anymore, it's actually the quantum energy, loss energy. So you can change it to E1 in this case, quantum case. Then you can formulate your potential too. Almost the same like this. So you can calculate the tunneling coefficient. So how many electrons pass through the barrier so that we have leakage current. Leakage current is not good for any devices. So you will see this problem so many times. And then let me just calculate that. So this exponent have this integral, so integral power is most important. And you have 0 pi over E epsilon, and then actually previously it was 8m, but I changed it to like this. Please note that 2m is now out of the there. Oh, okay. 2 is out of here, so it's right. So within the square root, only 2m is left, and another 4 within square root came out of the square root, and it is indicated here. Okay, so it is same with the previous equation, right? And then the integral. We put the square root to 2m, and then we put this one. The energy of electron is actually Fermi energy, EF. So V phi EF minus E epsilon x. And then you set the electronic energy at EF, then EF, they subtract with each other. Then we only have phi minus E epsilon x, and then dx. So it is actually rather simple integral. In this case, we set this one to be like y. Then when y is 0, when x is 0, y becomes pi. When x is pi over e epsilon, put it here, then y becomes 0, like this. There was square root of 2m, then square root of y, then what else? dx. So if we take dy becomes minus e epsilon dx. So dx becomes minus e epsilon dy. Okay, so minus goes here, it becomes e epsilon square root of 2m, and then if you move this here, there's minus sign, then we can change the order of integral from 0 to 5, and then you have y to the power of half, then dy. You take the integral. This is very simple, right? Everybody can calculate that, so please try it yourself. You can get this. This will be final exam problem, I guess. Okay, so please try it yourself. Okay, so almost that's it for this tunneling problem. You only need to calculate this t, okay, based on this WKB approximation. We studied the wave function calculations, but it could be quite complicated, so we just accept this one, huh? WKB approximation. And then from now on, application example, tunneling in LEDs. Actually, this is a case of gallium nitride LED, which is commercially available and dominating the market. In the case of gallium nitride LED, the potential structure is way more complicated than previous ohmic contact problems. So the details are explained in this paper, my old paper. And this is one of the important papers in LED studies, you will see. This is cited quite often. And here you will learn the electronic structures in LED. Yeah, so you can find many useful application examples from this paper. So wave function calculation, luminescence intensity, how can we measure those electrically and optically, those things you can find in this paper. So if we are working on LED, or if you could be working on LED, probably you will see this paper in the end. And then I just show the tunneling part of LED. Usually you use Contomel, but not just one. There are many Contomels, so we call it multiple Contomel. Multiple Contomel. So from Contomel 1 and Contomel 2, there could be tunneling. When you bias the sample, basically you connect the voltage like this. Then the potential is tilted more and more. Okay. Then eventually electron pass through only single barrier. It doesn't meet another Contomel anymore. It just pass through. So that's when tunneling is severe. Okay. And then we can formulate the potential barrier like this based on electric field EV in this case. then you put this into that WKB approximation. So almost the same, okay? The WKB approximation. Then you calculate the tunneling coefficient tau. Okay. Here actually I used tunneling time. I'm sorry. So this is actually 1/t, proportional to 1/t. This is tunneling time calculation. Previously we calculate transmission and they are inversely proportional with each other. People sometimes use this one, people sometimes use t, and they are inversely proportional. The details are introduced. It will be quite complicated. You might need a, what should I say, at least master degree to understand the paper. But at least tunneling part is simple. You just apply that WKB approximation mathematical formations. So I just want to show you that WKB approximation is still very useful in applications. And this is a little bit more than that, far above our scope, beyond our scope, but it could be useful in your future research. So here I'm measuring the decay time of electrons as a function of external voltage. So we are manipulating the decay time of electron. Here decay occurs because the electron hole overlap in space. If they are overlapped, they met with each other, then they disappears by emitting the light. So that's the idea of the LED. Then the emission time tau is formed by electron hole recombination, as I explained. And there is also something called tunneling. And there's something else like fermionic emission. This is another mechanism for leakage current, as shown here. So this is another important issue, fermionic emission. You will see these issues many times. This is another origin of device malfunctioning. This is formulated like this: quantum width, effective mass, KBT, the thermal energy, barrier height, and then thermal energy. So the ratio between barrier and thermal energy means like this. If it is like thermally activated, like if it is E1, but still we have room temperature, then the electron is not only staying here, it's thermally activated by taking the thermal energy KBT. And then this barrier height is H. So you compare H versus thermal energy. When H is very large compared to thermal energy, the fermionic emission is small. When the thermal energy is very large compared to H, then fermionic emission is large. That's the way we formulate this equation for fermionic emission. Others are like recombination time, tau r. Tau r is depending on wave function, electron wave function, and Hall wave function. And these are actually indication of wave function overlap. So this is another basic idea. Wave function is overlap very well in space. Then you got this very large value, large, and then the recombination time becomes small. Okay, they overlap quickly, so that emission time or recombination time is becoming shorter. So that's the way you calculate tau r, tau t, and then we calculate the total carrier decay time in semiconductor device. So this is basic idea in any samples, any materials. So it could be useful for your future material studies or device studies.